this result, this conditional, this probability of intersection of events is same as the product of this probability. This rule is called a multiplication rule. Later I am going to introduce the total probability rule, whereas this one is called a multiplication rule, that is for the probability of intersection of events is same as the probability of individual events. Now we are moving into the next important definition before going to the Bayes theorem, that is called a total probability rule, or we can give it as a theorem also. So this is called a total probability rule. What it says, let A1, A2, so on be a sequence of events in F such that AI intersection AJ, that is going to be empty. That means that they are mutually disjoint for all I is not equal to j. Not only that, if I make a union of AIs, that is going to be the whole set. That means indirectly this is the partition of omega. This sequence of events could be finite or countably infinite. Therefore, I am making a union of i's, union over I. It could be finite or countably infinite such that they are mutually disjoint. Union is going to be the whole set. That is basically a partition events. Indirectly, what we are saying is they are mutually exhaustive also. These events are mutually exhaustive, satisfying this condition. Then for any event capital B belonging to F, probability of B can be computed by the summation of conditional probability on AIs multiplied by P of AIs. This summation over I, provided P of AIs has to be strictly greater than 0. So the total probability rule says if you have a partition events on omega, the probability can be computed for any event with the conditional probability on partition events multiplied by the probability of those partition events for all i's. This is going to be called as a total probability rule. We can give the proof of this. Even though I made it as a definition, we can prove it. Any event B can be written as a B intersection whole set. That is same as we can rewrite event B intersection. The omega can be rewritten as the union of i's over i's, AIs. Then this is same as union of i's of B intersection AIs. Therefore, the probability of B is nothing but, since B intersection AIs are mutually disjoints, therefore this is same as summation of P of B intersection AIs. That is same as, you can apply the conditional probability, therefore it is going to be probability of B given AIs multiplied by probability of AIs. This is possible when P of AIs are going to be greater than 0. So whenever the P of AIs are going to be greater than 0, then probability of B can be computed summation over I P of B given AI is multiplied by the probability of AIs. Using this total probability rule, we are going to define a next rule that is called a Bayes rule as a next definition. That is called a Bayes rule. What this rule says, the continuation of the total probability rule, that is for any event capital B belonging to F with the probability of B is also going to be greater than 0. Already we made the assumption P of A is or greater than 0. Now we are making P of B also going to be greater than 0. In that case, one can find the P of the partition event AI given B, that is same as P of AIs multiplied by P of B given AI divided by summation over J P of AJ multiplied by probability of B given AJ. This is valid for all I, because we have already defined AIs are the partition events of omega. So you can go for finding the conditional probability of AIs given B provided probability of B is greater than 0. That is same as the numerator is probability of AIs multiplied by probability of B given AI, whereas the denominator is all possible values of the same thing in the numerator. Therefore, this ratio is going to be the probability of AI given B. You can prove it easily. The left hand side is same as probability of AI intersection B divided by probability of B. So in the numerator you can apply the conditional probability, and the denominator you can use the total probability rule. Therefore you can get the answer. So this is a very important result on whenever you know the partition events, you can find the probability of any event using a total probability rule, as long as you know the conditional probability on partition events and the individual probability of AI's partition events. Then using the same result, you can find out the conditional probability of partition event given any event B provided probability of B is greater than 0. We will go for the simple example. It is known that the population of a certain city consisting of 45% females and 55% males. Suppose that 70% of male of the males and 10% of the females smoke. Suppose that 70% of the males and 10% of the females smoke. The question is, find the probability that a smoker is male. Let me read the question again. It is known that the population of a certain city consisting of 45% females and 55% males. Suppose that 70% of the males and 10% of the females smoke. Find the probability that a smoker is male. Let's solve this problem by treating, let S be the event, be the event that a person is a smoker. Let M be the event that the person is male. F be the event that a person is a female. Let S be the event that a person is a smoker. M be the event that a person is male. F be the event the person is a female. Therefore, you can find the probability of M, that is 55%, therefore 55 by 100. Probability of F, that is 45%, so 45 by 100. And you can find the probability of S given male, that is 70 divided by 100. Similarly, you can find the probability of S given F, that is also given, that is 10%, therefore 10 by 100. These are all the given information. Now, the required probability is probability of M given S, that is same as probability of S given M multiplied by probability of M divided by probability of S given M multiplied by probability of M plus probability of S given F, probability of F. So, you can substitute all the values, then you can get the answer, that is 0.895. By substituting all the probability values, you can get the conditional probability of M given S. So, by using the total probability rule as well as the Bayes rule, we are getting the result of conditional probability of M given S. So, there is a very important result on using the Bayes rule, that is called a priori and posterior distribution. There is a very important concept on priori and posterior distribution. What it says, let A1, A2 and so on be a finite or countable partition of omega. That means intersection is empty and the union of A is the same as omega, with P of A is greater than 0 for all I. It is basically a partition events of omega. If B is an event, if B is an element or event in F with the probability of B is strictly greater than 0, then the distribution or the P of ANs for all n, that is called the priori distribution. Because this information is known to you earlier, therefore, this is called the priori distribution, knowing the probability of partition events for all n. That is, before B happens and the P of AN given B, this collection for all n, that is called the posterior distribution, because this distribution is known after B happens, whereas P of A and C is before B happens, therefore it is called a prior distribution, and probability of A n given B, that is after B happens, therefore it is called a posterior distribution, that is after B has happened. So, this is a very important result on probability, the prior and posterior distribution based on Bayes rule. The one is called the probability of partition events, these are all called the prior distribution, and after the event B happens, the probability of A n given B for all n, that is going to be called as a posterior distribution. This has the wide application in statistics. So, with this we are completing basics of probability, starting from random experiments, sample space, probability space, probability measure, then some results on the probability space, then independent events, then mutually independent and the pairwise independent events. Then after that we have introduced a conditional probability. Then we have introduced two important results. One is a total probability rule and the multiplication rule. Then finally we have discussed the Bayes rule.